All right, we're going to break this baby up into two. The other one was getting a little long, so we theoretically looked at the galvanic or voltaic cell for that zinc copper reaction. And I would just kind of want to show you the overall picture. We drew the galvanic cell with all the component parts and the two half cells separated. So we had the oxidation half cell occurring at the anode, right? So the zinc was oxidizing to zinc plus 2, giving the electrons that travel around. I want to kind of go through this before I build the actual cell. Now, there's some shortcut terminology you'll see a lot in electrochemistry. It's called a couple, and you'll see these couples a lot written in textbooks or in electrochemical tables, things like that, where they take the two components, but they just don't include the electrons in there. You can kind of figure that out from inspection. So here I've got zinc solid going to zinc plus 2, so they do a little backslash there. You can tell that it's losing 2 electrons, right? So that's called the zinc-ion couple. And then for the reduction half reaction from what we had the copper 2 ions, which were picking up the electrons that had traveled from the anode to the cathode, so they're on that copper metal, right? So the electrons were building up, they were coming from the zinc, traveling up to here, and then the copper ions struck it from solution and played it out as solid copper. So that creates the copper couple, the copper plus 2 going to the copper solid couple. Just some new terminology for you. If we add these two together like we've done before, now what's nice is the 2 electrons here and the 2 electrons there match. So when we add these together, the electrons automatically cancel out. So I don't have to multiply anything like we did with the silver one. We had to multiply the silver half reaction by 2 to balance things out. So they add up directly. So the electrons cancel out, so I get the zinc solid plus the copper 2 going to zinc 2 plus copper. And if I had done that in one cell, right, one beaker, the electrons would have been transferred directly and I couldn't get any useful work out of that. But if I put them in separate cells, I can force the electrons to travel around. So you're going to be doing this for a lot of stuff. And the tendency for those electrons to flow is called the cell potential, which we'll look at right after this. So what we're going to do is we're going to take our voltmeter and we are going to create this. So I've got a voltmeter here and we can turn that on. You know, we got alternating, direct, we can do currents, we can do voltages, whole bunch of resistance. So we're going to do voltage, direct voltage, and I'm going to get it to as many decimal places as I possibly can. And we've got a red lead, boop, and a black lead that come from our voltmeter here. Yay! So the red one always, when you're in lab, connects to the cathode, which is on the right-hand side of our galvanic cell. And the black lead, see our little alligator clips? Wow, wow, wow. That's going to connect to our anode. Boop, just like that. So in the anode, we have zinc sulfate. It could be nitrate, but we happen to have zinc sulfate solution in there, 0.1 molar, with our zinc electrode, the anode. And over here with our copper electrode, the cathode, I have copper sulfate solution. You want to try to get the heights about the same. As you can see there, and then I have my salt bridge with some potassium nitrate solution in there. So I got out, took a while to get all the air bubbles out, and I got these little cotton plugs in there. So this is my on-off switch. So when I have these 2 beakers and I pop this in there, boop, that allows the circuit to continue, and then you'll see the reading on the voltmeter. This is going to be tricky to do by myself. In this scenario. So I'm going to try to set this up as best I can. So I'm going to connect the black clip to the anode there. So I've got that connected. And I need to brace these wires because they're all over the place. And then I'm going to take the red one, connect it to my cathode. I'll have to hold these up for you. Let's brace that wire. So now I've got my 2 leads connected. You can see the 2 leads connected there. And now I'm just going to pop my salt bridge in there. That should be pretty easy. And then we'll be able to read. So you get nothing on there without the salt bridge, right? So let's take the salt bridge. I got my salt bridge. This will be challenging. I'll do the best I can. And I'm going to pop that in here. Boom. And that connects them, and we get a reading. You see that? So, depending on how well, this isn't the best galvanic cell I've ever put together in my whole life, right? But you can see the voltage there. I've got that connected. And if I take that salt bridge out, boom, it goes back to 0 again. All right, so that's essentially all you're doing. That salt bridge connects it, allows the circuits to flow. And if I had a third wire, I could direct those electrons out of here and do something with it. Pretty straightforward to do. So I'm going to pause this, put all my good stuff away here. And so that's an example of that particular one. And what I want to talk about is that number right there. Yes, where does that come from and what is that number? All right, gang. As you can tell, there's a lot of details to these electrochemical cells. You can write the overall equations, add the two half reactions together, look at couples. You could draw the whole galvanic cell diagram with the anode and the cathode and the salt bridge and the ion flows. And oh my gosh, expect to do that on exams. But wouldn't it be nice to have a shortcut for that? It would. All right, so we have something called cell line notation. A lot of people call these cell diagrams. I just call it line notation, where we're going to set up this equation, represent that whole gigantic picture of that galvanic cell using these couples, but instead of slashes, we're going to make these vertical lines that represent a phase boundary between like a solution and a solid, right? That would represent the difference. So, for example, in this case, at the anode, I have that zinc sulfate solution in there in contact with the solid zinc electrode, the anode. So we would write it like this, but just do a vertical line. And then the salt bridge, they like to use that, which separates the two half cells. They like to use two vertical lines. Sometimes you'll see those as dashed vertical lines. I don't really care one way or the other. So let me erase this board and show you this entire reaction and the galvanic cell all put together in a nice cell line notation. It's pretty sweet. All right, here's your shortcut, which is kind of nice. Cell line notation. Some people call them cell diagrams. Again, just a shortcut for drawing those gigantic galvanic cells and all these overall equations and whatnot. So we've got our two half reactions, right? In this case, we have the zinc going to zinc plus 2, giving off 2 electrons. And then we have the reduction half reaction with the copper 2 ions picking up 2 electrons and becoming copper solid. And we could represent that. So this kind of is like representing them as couples, except with a vertical line. So this represents that whole galvanic cell that we had, where we had on the left. Now, whenever you do galvanic cells or these shortcut line notations, always put the anode on the left-hand side and the cathode on the right-hand side. That's just how we do it. This is how we do it. Okay, anyway. So the solid and the aqueous solution are two different phases, right? So we're going to do a vertical line, and that represents that zinc solid electrode phase boundary, right? So we got the zinc solid, the zinc solution. Now, some people will write like zinc nitrate or zinc sulfate. All you need is the reacting species from the net ionic equation. If you don't know the concentration, just put AQ there if you're doing just a generic one. But we did know it for this particular scenario. We had the 0.100 molar, right, when we did it. So we'll write that in there. Okay, so I knew the concentration. For the salt bridge, that represents where the connection between the two half cells, we draw a double vertical line, and some people do dash lines. Again, I don't care which one way or the other. And then on the other side of that salt bridge, we had the cathode, right, where the reduction was going on. So we started with the copper 2 ions in solution, right, and they were the 0.1000 molar. And then we had the phase boundary to the solid zinc electrode. Pretty straightforward. Now, they can be complicated if we start getting gases and things in there. So if we have a gas, you can put the G with the pressure and whatnot. So what we're going to lead into is that number that we got on the voltmeter. What that potential, what does that represent? And then we're going to lead into kind of like what we did in thermodynamics. What if we're under standard conditions? And what if we're under non-standard conditions? And you'll see a huge amount of overlap with thermodynamics with the types of equations we're going to do and to relate them to spontaneity. Sweet. So let's take a look at cell potential real quick. All right, so this is the key to this chapter right here, this thing called cell potential. That's what we measured on that voltmeter when I put that together. It was, I forget what it was. Doesn't matter what the value is. We'll talk about what that means after we do this. But as a definition, this is a quantitative measure of that driving force that makes the electrons flow from the anode to the anode to the cathode. If you remember that first demo I did where I took a copper wire and put one in a silver ion solution, the other in a zinc ion solution, it happened spontaneously in the silver ion solution, but not in the zinc ion solution. So obviously there was a stronger driving force for electron transfer to happen with the copper solid with the silver ions than it was for the copper solid with the zinc ions. Actually, there was no driving force at all for that one. Numerically, we can measure that using what's called the cell potential, all right? So that is the potential difference between the two half cells, the driving force for electrons to go. You know, a bad analogy might be like a water flowing down a waterfall, right? So the higher, say we have a hydroelectric dam or something, the higher the height, the more potential there is and the more energy we can extract out of that, right? So think of the cell potential or the potential difference as the height of the waterfall between the two half cells, the two electrodes. That the greater this number, the stronger the driving force is for electrons to flow, the more likely that's going to happen. And of course, the more work we can get out of that as well. So we call that capital E sub cell. Right? So that's going to be the cell potential. A lot of people call that the cell voltage because we measure it in volts. So what I'm going to do is talk about the units on the next board here, and then standard versus non-standard conditions, and then we'll do another video specifically for that kind of stuff. All right, let's finish off this video with just kind of an overview of this cell potential. For spontaneous reactions, as you saw in that voltmeter, that reaction occurred, we had a positive value for E cell. So anytime you have a positive value or an E cell greater than 0, that means we have a spontaneous reaction. And we're going to see this come back and haunt us when we do some equations later, because remember, delta G was negative for spontaneous reactions, but E cells are positive. You're going to see these end up in the same equation later, I guarantee it. So that would mean a non-spontaneous process would have a negative E cell or an E cell less than 0. So if I had switched those leads on that galvanic cell, you would have had the same number, boop, but it would have been negative, right? It's just the opposite process. So the units for cell potential are called volts. That's why a lot of people call cell voltage instead, that potential difference, the driving force for the electron flow. And that's got the symbol capital V. I'm sure you've all heard about that if you've ever stuck a fork in a socket as a kid, or ridden your bike full speed into an electrified barbed wire fence, just theoretically. You get a feel for voltage versus current and all that kind of fun stuff. We'll talk about current in a little, probably towards the end when we do the forcing non-spontaneous processes to become spontaneous. We'll talk about current in that scenario. But volts is that potential difference, the height of the waterfall. So the higher the volts, the more positive it is, the higher that waterfall is. So a volt is technically a joule per coulomb. Joules we've run into before many times. That's an energy unit. And a coulomb might be something new for you guys. That's the SI unit for electric charge. Makes sense because we got electrons flowing around. So really a volt is just the amount of energy packed in per unit charge. And I think a single electron is like negative 10 to the minus 19th coulomb, somewhere in that range. I don't remember the exact number, so it's one electron is around negative 1 or 2 times 10 to the minus 19th coulomb. It's pretty small for a single electron. So obviously we're dealing with probably mole quantities of electrons when we're dealing with these electrochemical cells. So energy per unit charge, joules per coulomb. So a lot of times when we're doing unit line equations later on, instead of writing volts as V, we'll write it as joules per coulomb, so you can see coulombs cancel out or joules cancel out or something like that. All right, so we'll get into the next one. Let's take a look at, we're interested in the potentials for just the half cell. So this is the overall electrochemical cell. Is there a way we could break this down into just the anode or just the cathode? What do we do if we're under standard conditions, 1 molar? An activity of 1 or 1 molar versus non-standard. So the example I did was 0.1000 molar. That's not standard conditions. We're going to have some crazy fun with that. We'll see you in the next video, my friends.